vitamin B3 for NAD, which is niacin. Acetyl coenzyme A, in order to help make this product, we also have to have vitamin B1, which is thiamine. So if you've ever heard anybody say, oh, make sure you're taking your B vitamins so you can have plenty of energy, this is exactly why. Because in order to make enough ATP, you have to have enough of your B vitamins. If you want to be able to eat these from a food source, these come from deep green leafy vegetables. And I'm going to guess y'all don't eat enough of those because remember on that video where he said that probably to get people to eat enough of their deep green leafy vegetables, we'd have to pay them. So probably don't have enough of those in our diet. Now, by the way, one other thing that I want to show you here is, in order to make acetyl coenzyme A, we can use carbs. So like our glucose and fructose, we can produce acetyl coenzyme A. But also to make acetyl coenzyme A, we can use fatty acids, and they produce acetyl coenzyme A. Breaking down proteins, and they turn into acetyl coenzyme A. So it doesn't matter what type of macromolecule, carbs, fats, proteins, we're all eventually going to break them down into acetyl coenzyme A. Remember when we talked about fatty acids and I told you in the fatty acid chain you take 2 carbons at a time and turn those into energy? Well, acetyl coenzyme A happens to be a 2-carbon molecule. So these 2 carbons are actually what we're turning into the acetyl coenzyme A. And then, of course, acetyl coenzyme A is going to go into your citric acid cycle. And then from there, which is what we're going to talk about next, we're going to go into what's called the electron transport chain. Now, the electron transport chain, sometimes you'll also hear people refer to this as the chemiosmotic theory, or they'll talk about this as oxidative phosphorylation. We're really going to talk about it mostly as the electron transport chain in class. But this is happening inside our mitochondria. So I want to take a couple of seconds and talk about the structure of the mitochondria because this becomes very important in ATP production. So our mitochondria, this is just one that's chopped in half so we can see the inside of it. It has 2 layers to it, or we can say it has 2 membranes. So basically you have a mitochondria that has an outer membrane, and then we have an inner membrane. Between the outer and the inner membrane, there is a space which is referred to as the inter. Inter means between. The intermembrane, between the membranes, this is a space. So we have the intermembrane space. And then there's a space directly in the middle, and this is called the matrix. This is where they filmed the movie. Okay, now, when we talked about the intermediate step, and we talked about the citric acid cycle, both of those steps were happening in the matrix, okay? So we have the intermediate step, and we have the citric acid cycle. They're both occurring in the matrix of the mitochondria. Okay, so let's take a look at the overhead for a second. This is the outer membrane in this dark orange color here. And then you have the inner membrane in the yellow. And then in between these 2 membranes there is this opening or this intermembrane space. And then in the middle, you have the matrix of the mitochondria. Now, both the inner and the outer membrane of our mitochondria is just like our cell membrane, made up of a phospholipid bilayer, integral proteins, all that kind of good stuff, okay? Okay, so this entire chain right here is what we refer to as the electron transport chain. Now, this chain is found on the inner membrane of the mitochondria. So you have this chain, and you have multiple chains like this all over the inner membrane. So you have hundreds of these electron transport chains all throughout this inner membrane. So this region right here is what we would refer to as the inner membrane. Okay? So then on either side of the inner membrane, we have some type of space. We have an intermembrane space, and we have the matrix. So if you remember, the matrix is in this region, and then here we have the intermembrane space. So which one I want to call this. We'll call this region here. Let's call this the intermembrane space. And we'll call this the matrix. Okay. Now, there is a difference in concentration of hydrogen ions in the intermembrane space versus the matrix of the mitochondria. I can't remember which way I want to do this so I can make it look appropriate for you. Yeah, that'll still work. Okay, so in the intermembrane space, there's a very high concentration of hydrogen ions. In the matrix, there are some hydrogen ions, but it's a much lower concentration. Not as many hydrogen ions. Now, in this inner membrane, we have multiple integral proteins. And each of these integral proteins, except the last one, is what we would refer to as a cytochrome. So CYT stands for cytochrome. And a cytochrome is a protein that contains iron. So in each one of these cytochromes, in these proteins, there is an iron sulfide component. So it's actually an FeS that these contain. So each one of these cytochromes, each one of these proteins, has iron sulfide in it. And each one of them contains a little bit more than the one before. So this first cytochrome is called NADH dehydrogenase. It does not have as much iron in it as this second cytochrome, which we call Q. The third cytochrome is cytochrome BC1. It has more iron than Q or NADH dehydrogenase, and so on. This last one is not a cytochrome. This is just an enzyme. This is called ATP synthase. It does not contain iron. Okay, so now we're going to use NAD and the two hydrogens that it was able to pick up from glycolysis or the intermediate step or from the citric acid cycle. See? And we're bringing that NAD with its 2 hydrogens into the matrix of the mitochondria. That NAD has a very high affinity for this first integral protein cytochrome, NADH dehydrogenase. And because it has such a high affinity, this is going to be pulled towards this first cytochrome. Now, because the cytochrome contains iron, it also has a very high affinity for electrons. And remember, each one of these hydrogen atoms has a single electron. So as NAD gets pulled closer to this first cytochrome, the iron is going to steal the electrons. It's going to strip the electrons off of these hydrogen atoms, and our electrons are going to integrate, become part of our first cytochrome. So the 2 electrons are going to be stripped off of each of the hydrogen atoms by the iron in NADH dehydrogenase, or our first protein. That means those 2 electrons become part of this first cytochrome, and since the hydrogen atoms have lost their electrons, they now become positively charged hydrogen ions. Now, by the way, just so that you know, this is a potential essay on your first exam. You have 2 potential essays on your first exam. The first one is explaining how the electron transport chain works. The second one will be explaining how protein synthesis occurs in both transcription and translation. All right, so one more time. We're originally bringing NADH plus H, 2 hydrogen atoms, into the matrix of the mitochondria. They come from glycolysis, citric acid cycle, intermediate step, and the NAD is attracted to this first protein, cytochrome. As the NAD gets closer, the iron now is able to strip the electrons off of the hydrogen atoms. Those electrons become part of this first complex here, and the hydrogen atoms are now left with only a proton, and so they become positively charged. Now, it just so happens that NAD is also positively charged. So now what will happen to this molecule? They're going to break apart because positive charges repel each other. This molecule is going to completely fall apart. NAD, the 2 hydrogen ions, they're all going to separate from each other. As a matter of fact, when they do, NAD just says, okay, well, I don't have anything to do here. I'm going to recycle. I'm going to go back to glycolysis, back to Krebs or citric acid, back to the electron transport chain so I can pick up 2 more hydrogen atoms. So this NAD here is gone. It goes back, it does its job again, and we're left with just the 2 hydrogen ions. So the NAD is going to be recycled after it repels from the hydrogen ions, and these hydrogen ions are just going to stay right here in the mitochondria. So this one, gone. Any questions so far? Now, these 2 electrons that have entered into this protein, when these 2 electrons come into this protein, they're moving really fast. Electrons are moving at the speed of light, which also means they have a lot of kinetic energy. So to transport from these hydrogen to the protein, they're doing it really fast with lots of oomph to them. Which means that when these electrons enter this protein, they have the ability to break some of the hydrogen bonds so that our protein will change shape. That shape change actually causes this protein to turn on, and this protein happens to be a pump. This pump has the ability to actively transport our 2 hydrogen ions from the matrix into the intermembrane space. Okay, so again, the 2 electrons, their job is to use their kinetic energy to change the shape of our pump and activate that pump. And now with active transport, we're going to transport our 2 hydrogen ions from low to high concentration from the matrix to the intermembrane space. again, we have our 2 electrons that are in this first cytochrome and bringing with it kinetic energy to break some hydrogen bonds in this protein, change its shape, which then activates the pump. Now we're going to actively transport 2 hydrogen ions from the matrix to the intermembrane space. Any questions? Now, as soon as this happens, our 2 electrons are going to be on the move, because cytochrome Q has more iron on it than NADH dehydrogenase. So cytochrome Q has a greater affinity for our electrons than this first protein. And our electrons will immediately jump over to cytochrome Q. So again, cytochrome Q, or what we call ubiquinone, has a greater affinity for the electrons than NADH dehydrogenase, and so the electrons move over to Q. Now nothing else happens because Q is only kind of like a stepping stone, and as soon as the electrons move, they're going to move again. So we have these electrons moving to cytochrome Q. Now the next cytochrome, cytochrome BC1, has a greater affinity for the electrons than cytochrome Q because cytochrome BC1 has more iron. And so what we're going to see is these 2 electrons are now going to jump to cytochrome BC1. Now when they do that, you're going to have the same thing that happened in this first protein. The electrons are going to use their kinetic energy to break some hydrogen bonds and change the shape of this protein, which also happens to be an active transport pump. And we're going to have 2 hydrogen ions actively transported from the matrix, again, into the intermembrane space. these two hydrogen ions, what we're going to see is these electrons are going to be on the move again. And now we have cytochrome C. And cytochrome C has even more iron in it than cytochrome BC1. And so these two electrons now have a greater affinity for cytochrome C, and so they move to C. Now C is, again, like Q, it's only a transport protein. And so we don't have any pump or anything going on here. And the electrons aren't going to stay for very long because now they're attracted to cytochrome oxidase. And cytochrome oxidase has a greater affinity, more iron, and our two electrons are going to move to cytochrome oxidase. So our two electrons have moved now to cytochrome oxidase due to its higher affinity. And this is a pump. So when those electrons move there, they're carrying the kinetic energy, which breaks hydrogen bonds, changes the shape of the pump, and the pump becomes active. Now we're going to be able to actively transport two more hydrogen ions from the matrix into the intermembrane space. Any questions so far? So notice what we've done so far is we've turned on 1, 2, 3 active transport pumps. And how we turn them on is we use those two electrons. Those electrons activated this pump. And the whole idea of turning this pump on is so that we can move 2, 4, 6 hydrogen ions into the intermembrane space. We want to have an even greater concentration now in the intermembrane space than we had before. Now, these 3 pair of hydrogen ions have the ability to now just simply diffuse from high concentration to low concentration. And they're going to diffuse 2 at a time. So we're going to take our first pair, and they're going to diffuse through this ATP synthase from our high concentration to our low concentration. So now the reason that these hydrogen ions are going to diffuse through the ATP synthase enzyme is to cause that ATP synthase to spin. So like you saw in the video I showed you, there's spinning of this enzyme. That spinning brings together an ADP and a phosphate, and when two hydrogen ions diffuse through our ATP synthase, we make one ATP. Now remember, we just actively transported 1, 2, 3 pair of hydrogen ions into this intermembrane space. So we're going to have all 3 pair of these hydrogen ions diffuse through the ATP synthase so that we'll be able to make 3 ATP. Remember I told you for every 2 hydrogen ions that this NAD carries, we make 3 ATP from this. Any questions so far? Okay, so now one other thing we need to talk about before we move on are these 2 electrons on our cytochrome oxidase. We need to get them out of there if they need to leave, because the next NAD is going to come along and drop off its next 2 electrons. And if there's 2 electrons still here, the next ones will back up to cytochrome C. And if we bring another one in and we don't get rid of those, the next electrons will back up to the next protein, back up to Q, back up to the next protein, and then the chain is just clogged. So you have to get rid of those 2 electrons. Well, it always turns out that oxygen is hanging around this electron transport chain because remember, in the mitochondria, we're aerobic. Oxygen has a much greater affinity for electrons even than iron. And so these 2 electrons will immediately be pulled towards and bind with our oxygen. So basically we have something like this. We have 1/2 O2, and we're going to add 2 electrons to it, and we're going to get an oxygen that has 2 negative charges attached.
Why is it 1/2 oxygen?
Because that's a single oxygen atom. I could do it differently and I could wait till 2 more come in and I could have an O2, but it's the same thing.
Oh, I see. Let's do that. Gotcha.
Now, this negatively charged oxygen is hanging around where our hydrogen ions come out. And so what's going to happen is the negatives and the positives are going to attract. So you're going to end up with 1/2 O2 that has the negative charges binding to 2 hydrogen ions, and you'll create water. So you're able to get rid of these electrons, and you end up with 3 ATP molecules and a water molecule. Any questions so to you about as far as these electrons are concerned. Very interesting, true story. There's this guy who, no lie, he has 5 PhDs. And I don't know why, but he does. He's got 5 PhDs. And one day he's sitting at his house in La Jolla, out by San Diego, drinking a glass of wine. And he's thinking about the electron transport chain. I don't know about you, but that's what I think about when I'm drinking a glass of wine and sitting by the beach, the electron transport chain. Anyway, so he's thinking about this. And as he's thinking about this, he's thinking about these 2 electrons right here. And one of the things he's thinking is, what if the person was like really low in oxygen? Maybe they just didn't have enough oxygen, maybe they're running a lot or whatever, and they're super low in oxygen. What would happen with these electrons if oxygen wasn't around to bind those 2 electrons and then turn everything into water? Could those electrons, since they're so high energy, could they escape this protein and get out into the cell? Because if they could get out into the cell, you could think of these electrons like a ping pong ball, just moving around super fast in the speed of light throughout the cell, and they would have the ability, if they could do that, to hit our DNA and cause the DNA to break and mutate and create cancer. And so he thought about it more, and he thought, this is a pretty good theory, pretty good hypothesis. I really like this. I'm going to believe that this is true. And I'm going to call these electrons free radicals. And I'm going to say we have free radicals in our body. And so he went around telling all his friends about his new free radical thoughts. And other people thought this was really brilliant. And he put it all down on paper, and a lot of other people heard about it. He even got onto the Oprah Winfrey show. And before you know it, now that he was on Oprah, you know it has to be true. And he was in newspapers, and he ended up in all over other television shows, and it's in your textbook too. His theory is in pretty much every physiology textbook in the world. Now the interesting thing about this is, the dude was just sitting around drinking a glass of wine one day and came up with this thought, and now it's in your textbook as if it's 100% accurate, but there's 0 scientific evidence to prove that he was right. Probably not a good idea to put that in your textbook yet, but sometimes these things happen because, you know, Oprah said it, so it must be true, right? So some scientists decided, well, you know, maybe we should do an experiment on this and see if maybe he's right. Good idea, right? So here's what they decided, because his whole thought was, what if there isn't enough oxygen in this person? Then these electrons can get loose and wreak havoc. So what kind of people are low in oxygen? Cigarette smokers. Exactly. So what this group did is they took 500 people who smoked cigarettes, and they put them into one group, and 500 people who did not. And all they did was ask these 1,000 people to please take these anti-free radical vitamins every morning. Now you've heard of anti-free radical vitamins, I'm sure, you know, beta-carotene in your vitamins, things like that. You know, they're supposed to really help you. That's all they had to do. That was the whole experiment. Please take these vitamins, because these anti-free radical vitamins are supposed to grab a hold of any electrons that are bouncing around in the body and get rid of them. But within 3 months, they had to stop the experiment, because in the cigarette smoking experimental group, 50% of that group, that'd be 250 people, were dead. They had died from just taking vitamins that were supposed to be anti-free radical vitamins. So what that would say to me, and what it says to a lot of people, is there's got to be a little bit more to this story than what the guy was theorizing one day while drinking wine. Must be a little bit more complicated than what he's thinking. Because if those vitamins killed those people, something interesting and different is going on. And of course, you can't repeat that experiment. I mean, there's just absolutely no way. And we don't have really any cigarette smoking animals, okay? We can force them to smoke cigarettes, but nowadays, that's pretty much a no-no. In the good old days, you could force anybody to smoke a cigarette. It's really easy to force chimpanzees to smoke cigarettes. They got hooked just like that. I actually know a chimpanzee who, he bit off a guy's leg because the guy would not give him his pack of cigarettes. He was trying to wean him of his cigarettes, and the chimpanzee waited for him, hid around the corner of his cage so the guy couldn't see him, and when he came to deliver his food, grabbed him through the food tray opening and literally bit his leg off because he wanted his cigarettes. It took him some serious addiction. And we're not allowed to give them cigarettes anymore, so they cannot repeat this, but it would only mean there's something a little bit more to this whole concept, this whole idea. Which, the reason I tell you this story is because it's so important for you. There's a lot of research that goes on out there that you're going to hear about in the hospitals first and foremost. And you don't always want to jump on the very first research project or the very first statement that comes out. Sometimes you need to sit back and wait and see, is this really true? You know, maybe they need to do a little bit more research on this before I'm willing to take this drug or I'm willing to believe this. You cannot be gullible, and let me tell you, you cannot believe what the news is telling you. Okay? It's really quite sad. And it's in your textbook. And they, even after this experiment, they still haven't taken it out of the textbooks yet. And you still see it on advertisements. They still sell anti-free radical vitamins. I'm not sure I want to take those personally. Maybe if they had done the experiment for longer, maybe they would have affected the healthier people who didn't smoke. I don't know. Maybe it would have made them feel better. I don't know. But I'd rather wait till somebody else figures it out and they don't use me as a guinea pig. Just personal opinion. Any questions? Okay, real quick, one more thing I need to show you. There is another protein here. Really doesn't have anything to do with NAD, so that's why I didn't draw it there to begin with. But this protein has a very high affinity for FAD. Remember, in the citric acid cycle, we also have FAD. So when FAD comes into the matrix with its 2 hydrogen, it's going to be attracted to this succinate. And the same thing that happened in the beginning with NAD is going to happen again. The iron is going to strip the 2 electrons off of our hydrogens. And we're going to end up with positive charged hydrogen ions. And FAD is also positively charged. So they're all going to repel. And FAD is going to leave the scene. It's going to go back to the citric acid cycle. These 2 electrons then, okay, watch, they're going to be attracted to Q. They never come in contact with this first pump. They don't have anything to do with NADH dehydrogenase. Instead, they go from succinate to cytochrome Q, and they only activate 2 pumps, which means we'll only actively transport 2 pair of hydrogen ions through our 2 pumps, which means we'll only have 2 pair coming through our ATP synthase. We'll only make 2 ATP. So if you were to get this as an essay, what I would want you to write for the second part is just that FAD is attracted to succinate, and the electrons bypass the first protein. Only activates 2 pumps. You only make 2 ATP. Excuse me. You don't have to go through the whole process and every single step. I just want you to tell me it's attracted to succinate. The electrons go right to Q. We don't activate the first pump. We only activate 2 pumps. We only make 2 ATP. Any questions? All right, so one last thing. As far as what I've written up on the board, okay? Those are notes. That is not your full essay. I said a whole lot more than I wrote. So if you were to write just what I wrote, you'd probably end up with a D on your essay. So you need to kind of fill in the blanks, flush it out, be able to write it in more detail than what I wrote. Okay? So do not assume that that is enough writing for an essay. Also, I'll write your essay in steps so that it's easier for you to memorize. Put numbers by it. You will not. You do not get to write it in a flow chart. You do not get to write it with numbers. You get to write it in paragraphs with sentences. If I see it numbered like that, or I see you write it in my own words, I'll just give you a 0. I even had students who recorded the essay and memorized every single word I said and just wrote that. I don't know how they did it. It's pretty amazing. I don't want to hear what I have to say just spit back at me. What I want to hear is what you learned, what you know. And when you're writing this essay, how I want you to write this is as if you are teaching someone who is in a physiology class and has never learned about the electron transport chain before. I want you to be able to teach them. So my suggestion to you is go home and try to teach somebody this. I don't care who it is. I mean, you know, when my kids were younger, I used to pay them to sit on the couch and shut up while I talked to them and taught them these things. This is how you learn. Let me tell you, the saying is, if you don't know it, you can't teach it. Which also means if you can't teach it, you can't write it in an essay either. And if you do try to teach it to somebody, they're probably going to say, I don't understand what you just said. Which is a good thing because it's probably the part you're weak on and you need to go back and study. If you write it out and you don't have anybody you can speak it to, if you write it out, have somebody in this class read it. Or have somebody that, you know, is in your family read it. They don't have to be experts. But if they can understand it, you're doing pretty dang good. If they can get the gist of it, then you're writing a really good essay. If they don't get it, then it's probably you, not them.
Would it be okay to use pictures or diagrams?
No. No pictures, no diagrams,
What about to
nothing.
help ourselves out?
For you, absolutely.
Okay, so you don't expect us to draw that?
Nope.
Okay.
Not at all. I'm not going to ask you to draw it, just ask you to explain it.
It's just like explaining this thing to the person that doesn't know anything about this.
Yes, that's right. Any questions? It's a good time to ask. Yes.
So do we need to explain what the cytochrome is and
Yes.
where it comes from?
Yes.
Okay.
Because if you're explaining it to somebody who's never learned this before, they don't know what a cytochrome is. They don't know that it's a protein that has iron attached. If you're telling them that it's actively transported, you probably need to tell them what active transport means. So you could put like active transport, parentheses, movement from low to high concentration. Don't assume that you are writing your essay to somebody like myself who will understand this. Because I'm going to pretend when I read your essay that I know nothing about the electron transport chain, and are you teaching it to me? That's what I'm looking for. Do you know enough to teach me? So if you're wondering if you should put it in, put it in. Don't shortcut yourself. Write it. You'll have plenty of time, because what we're going to do for the exam, for exam 1, you'll have 50 multiple choice questions, and then you'll have some fill in the blank, and then you'll have your one essay. Your one essay is worth 50 points. Okay?
Well, can you say that for me?
Yep, I sure can. You're going to have, did I say 50?
50.
Yeah, it's a 50 question.
50 or 100.
I'm sorry. Let me start again. You're going to have 100 multiple choice questions. You're going to have some fill in the blank. And then you're going to have an essay that's worth 50 points. And again, that essay may either be what we went over today, which is the electron transport chain, or what we're going to go over on Thursday, which is protein synthesis, and we're going to talk about the process of transcription and translation. Any questions?
Same rules apply for the essay. If we abbreviate, then you need the,
Absolutely. Now what you can do is if you want to abbreviate, like let's say that you haven't written out what ATP is yet. So you're going to abbreviate ATP. You can put it in parentheses right next to it, and then you're good for the rest of the essay. So you can either do a legend or you can do parentheses. I don't care. It's totally up to you. Any other questions?
What about the glycolysis and the citric acid cycle, is all that, we have to draw that out on test as well? Or is that not gonna be on there?
Well, what did I say today about there's a really high probability you would see that, and then I just said that there's going to be some fill in the blank.
Okay.
So without coming straight out and answering you, let me just wink a little bit, okay?
That helps.
I'd study it if I were you. That's what I would do.
You're particular with grammars,
I think she means like punctuation.
punctuations and everything.
Am I particular with it?
With grammar, yeah.
Well, if it's like, I can't find a period at the end of your sentence, yeah, I'm probably not going to be happy about that. But if you like put the comma in the wrong place, yeah, I'm not even sure if I would know where the wrong place was. Okay, so I'm not an English teacher, all right? So I'm not going to kill you on that, by any means.
Is there, I mean, I know it's obviously going to be lengthy, there's 17 steps, but is there like a length requirement?
Nope,
Okay, just explain it. Okay.
nope, just get it done.
Okay.
Now, also, I'm going to warn you right now, I read every word you write. I read every page, every word, every time. And I've had students who have done things like write the first page, maybe the second page, and then they start writing about their dog. And then on the last page, they finish up the essay. Yeah, I'm going to read the stories about the dog. I even had a student last semester, it was so cute, he goes, I'm sorry, Dr. Harvey, I wrote as much as I could, and now I'm just going to tell you about my dog because I know you're going to read this. Okay? And he told me a little story about his dog. He had a little chihuahua he was all proud of. He goes, and at the end he says, I'm really sorry, I just couldn't remember anything else. He just had a brain fart. Okay? So I'm going to read it. If I make you write it, I'm going to read it. Okay? So just rest assured. So if you have a funny story you need to tell me, I'll read that too. Okay?
It's therapy.
You would be surprised. I'm not going to bring that up, but I have had some interesting stories. Anything else?